Alrighty, let's see what we got here. Stone game, medium. Alice and Bob play a game with piles of stone. There are even number of piles arranged in a row. Each pile is a positive integer number of stones. So it has to be at least one. The objective of the game is to end with the most stones. The total number of stones across all piles is odd. So there are no so there are no ties. Sure. Alice and Bob takes turn with Alice starting. Each turn, a player takes the entire pile of stones either from the beginning or the end of the row. This continues until there is no piles left, at which point the person with the most stones wins. Assuming Alice and Bob plays optimally, return true if Alice wins, false if Bob wins. Alice starts first, can only take 5 or less 5. She takes the first 5, so she prevents Bob from taking the 4. But Bob doesn't care because Bob would take the 5 anyways. Why would Bob take the 3? Bob takes the last 5, yep. And Alice takes the 4, wins with 9 points. Yeah, so even if Alice takes the last 5 to start, Bob would still take the first 5. Here, Bob would take the last 3. Or sorry, Alice would take the last 3 to start. Bob would try the 3 because taking the 2 is worse. And both of them reveal a 7 anyways. So Alice wins. Backtracking. Okay, so this is very similar to a problem from yesterday. Here, backtracking with 500 depth is just too long. Is it just too long? Wonder if it being odd. Okay, let me try. Let me try. This does seem like a variation of the last one, and I had assumed the last one was backtracking, but this one seems to be much longer. I'm not sure. Much longer in terms of like the 500 long pile length is would make the backtracking to be like 2 to the power 500, which is too big. To the power of 20 is like a million. But yeah, there's no way that this is backtracking. Like I'm pretty sure this would time out. Each pile is 500. I wonder if the earlier one was like there could be ties. There wasn't a restriction on having just odd piles or odd total. Um, an odd total. Huh. Both play optimally. 5, 5, 3, 4. 5, 5, 3, 4. Can't be greedy approach. Can't just take the biggest one of the options each time. Uh, 3723. Take the 3. I guess you could find the sum of all the numbers. The winner has to have a sum that's greater than half. So if at any point you have an option to take a value that pushes your total to be bigger than that, then you can immediately return. I guess that's a play. Does that, I don't know if that really narrows down the branching or narrows down the search all that much or terminates searches all that much. Maybe. Hmm. Alice and Bob takes turns. Beginning or end. All right, we're pretty sure this is the same. I mean, the previous solution should work on this thing. Nums here is called piles. But I'm pretty sure this is going to time out. Yeah, times out. Ah, I wish it would just had like stone piles or whatever. Stone or what was the previous naming? Predict the winner part 2 or something. Because it's clearly the same as the previous one, but just higher depth. And that does prevent backtracking. All right. I'll wonder. Okay, so I think maybe I'll do min score or minimum win score is equal to the rounded up version of the. Actually, I guess I could just do half plus 1. So it'd be the sum of all the values in the piles plus 1, divide by 2 plus 1. I could also do plus 1 divided by 2. Um, so if the front equals back, recursive case, if scores plus equals, so I can tell here if they win immediately, if they have the min win score. So I can do if scores of this player is greater than or equal to the min win score. Actually, I guess I can just do greater than and just not have plus 1 here. Oh, that doesn't make sense because the min is just it's not that. Minimum should be inclusive. Um, Scores for this player removes this pile. I'm assuming people have seen the previous daily. and then return the win player, which is the current player. No, sorry, return the turn. Because this player is definitely winning. Maybe I should do that. Yeah, this is not how I want to do it. Maybe it's just an ambiguous case. So if taking first or last option causes immediate win, higher than or greater than or equal to the min win score, or I guess player score, return. So I think this should be if scores for this turn plus piles up front is greater than or equal to min win score, or scores of this player plus piles up back greater than or equal to min win score. Return whatever turn this is. Okay, and then these two recursive cases are where it's indeterminate based on that. So it doesn't increase over the min win score. I have to do the backtracking checks or backtracking kind of analysis. Okay, let's see. I assume this would work still. Or not score is not defined because it scores. Yeah. Let's see if it does a time limit one within some reasonable amount of time. Possibly not still. Yeah, still too long. Interesting. Um, so how many words is this? Or how many piles is this? Probably like 30, 50. Okay. So that's not even close to being 500. Okay. Do. Even number of piles ranged in a row. And with the most stones, total number of stones across all piles. Take it from the front or the back. You can take half the piles pretty much. You have at least half the total. Wonder if there's like a binary search way. Recursion. Yeah, recursion here would not work if it's like an exponential branching, or if it's a branching factor that's different than one. Um, like if somehow recursion could just recurse all through the 500 length, but choosing between the first and second means that you're recursing between two options. No more piles are left. Take the 5. You're either left 3, 4, 5 or 5, 4, 3. Piles is 1 through 500. I mean, in the very specific case where your options are the same, then you don't have to recurse both ways. Like if you recurse, if you're, no, that's not true. That's not true at all. Just taking the first 5, you reveal 3. Taking the second 5, you reveal 4. So you do have to recurse both ways. It's just that your current score is not gonna, your score is gonna increase by a certain amount. It's not gonna increase by two different amounts between the possibilities. Yeah, okay. And you're not necessarily going to always take the one that even reveals the bigger number or the smaller number. How to do so, how to do so. 5, 3, 4, 5. You take some of those numbers to 17. Some of those numbers is 17. You need at least 9. Take a 5. Take a 5 from the back because that reveals the 5 to 4 as the next options, and you're guaranteed one of those two. But then maximizing, minimizing, maximizing, minimizing. 3, 4, 5, 5. 3, 4, 5, 5. Take a 5. Have a 3, 4. I wonder. 3, 5, 5. 5, 5, 5, 4. 5, 5, 5, 3. Huh. So you take a 5, take the front 5, you take the back 5. Take the front 5, you take the back 5. Take the back 5, you take the front 5. Hmm. I wonder. I wonder if it's not iterating over the same set of indices. So if player one takes the front and then player two takes the back, then the front and back indices are now at one and two. Maybe I need to store information. I need to store I need to store the results of certain inputs, because then it's possible that it redoes that calculation later on if the order is slightly changed. If I store like a table of front, back, and output, the front index, the back index, based on those two, the turn is can be fixed. So it's not like that's a new variable. Um, I store based on the front back the return value of that. Then I can just look that up in the table instead of recalculating it later on. And for every front back, there's only like n choose two different possibilities there. Okay, maybe that is the trick here, because maybe the thing that's tripping me up is the fact that it's doing every calculation repeatedly or doing some certain calculations repeatedly. Okay, but maybe I just have a results mapping. Say results table. I guess I'll just use a dictionary here, a default dictionary maybe. No, just a dictionary. There's no defaults here. And this is going to, this will store um, results based on where the key is the front and the back indices, and the value at that index, or value at that key is going to be winner. Okay, so here I can say if the front back tuple is in the results table. Oh, I wonder if I can just use cache. I think I can just use cache, right? So, yeah, I don't see why I can't. Um, was it cache? Uh, what is that called? Operator? Python method? Decorator? Decorator. All right, let's see how this goes. Yeah. So that fixed the timeout issue for that 50 long pile. Interesting. and did it wrong. So player 1 would take 10. Player 2 takes 8. And then player 1 takes 8. So player 1 should win. Why does player 1 not win here? Because of this thing, actually. Scores at turn plus piles up front. I mean, I assume this must be the thing that's tripping up this algorithm. Because it's the only addition that I had in my code. Nope. It just doesn't work. And actually it doesn't work for the other cases now. Okay. Yeah. I think I know. Sucks. It's the fact that I had ties go. Well, did I? So I was comparing scores before to determine who won. Scores at 0 is less than scores at 1. Player 2 wins. Scores at 0 is less than scores at 1. That should work even in the odd total case. Huh. 3. Okay, I should probably just trace this here. Yeah, okay, so it goes 0, 0, 0, 0, turn 0, 0, 0, turn 0. Gonna do recursion where the first player takes pile 3, front pile, has 3 score. Oh, it's 0, 3, not 0, 0. And then it goes to player 2. Player 2 is going to take the 7. Goes back to player 1. Player 1 takes 2. Goes back to player 3. Hmm. Okay, maybe I can't cache it. No, why can't I cache it there? Okay, let me go ahead and just print out the things. Um, I think maybe caching is not, it's actually cutting off some stuff I need to repeat in terms of execution. Yeah, it's gonna time limit exceed, fuck. Um, I'll do, say if length of the piles is greater than 10, just return 0. So it doesn't give me time limit exceeded. Okay. 0, 3, 0, 1, 3, 1, 2, 3, 0. So there has to be some repetition here, I think. 0, 3, 0, 2, 0, 1, 0, 0, 1, 3, 1, 2, 1, 1, 2, 3, 2, 2, 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, 2. 2, Yeah. I see. It could be it could be down to one single value, but the order, the path getting there is the path getting there is different. So therefore the value that the player has at that point is different. Yeah. So therefore the return value is going to be different. Okay. Huh. Is that so? Is it? How did I handle that? Because I think caching is generally correct, but maybe I'm wrong. Maybe I'm wrong about that actually. Because if I get a case where if I get a case where like one player takes the front the very first and the second player takes the very back, and I cache a result of like front is 1, back is n minus 2, that's a different path than if the first player takes the back one and the second player takes the front one and try to find the result. Oh boy. I mean, I guess it's true. I guess it's true that if you've reached this point before, I guess it's true that if you reach this state before and you've gotten a higher score total at this state, like let's say you reach the point where the front index is 5 and the back index is 10, and the score that you had was 20. If you reach that same state where the front index is 5 and back index is 10 and your score is like 15, 20 is better than 15, so you shouldn't evaluate that because it was strictly better before. So so what does that mean? Okay, so that means I need to have a more more information. So the I should store the front back. The value should be like there should be two things. It should go to a tuple that is who is your highest score up to this point. Your highest score up to this point and whoever wins. Yeah. Okay, so it can't be just a cache because it has to update that. So so the use results table if possible. So this should be something like if the current state front back is in the results table. And then secondly from that, if results table at this front back state the score within that for this player is greater than or equal to this current score. Hmm. Well, is this logic correct? Actually, I'm not sure if this logic is correct, because even if you reach this state on a previous iteration, with a higher score, your opponent could try to reach this state with you having a lower score. So the opponent forces you to have this state that has a lower score. So you can't. So maybe it should be. Maybe it should be only evaluating when you reach the state at a lower score. Maybe you should be lowering the score rather than raising the score when you do analysis. So you discard the high score and you actually keep the low score track because that's the one that your opponent would try to force you to do. I think. Or maybe that's just faulty logic. Like maybe what if the point just has two bad options, right? So 5, 5, 3, 4 versus 5, 5, 3, 4. So if it was something like the piles were 5, 3, 4, and 100. So if you player one, if Alice takes the 100 and the opponent takes the 5, then Alice would be at the state of like 1, index 2 with a score of 100 versus if Alice takes 5 and the opponent takes 100, then Alice is going to be at the state of 1, 2 with the score of 5. So here the correct state that Alice should be evaluating is the one where Alice takes the 100, because the opponent can't actually force Alice to take the 5. So maybe it's just not consistent. Maybe it's not consistent. You reach a state with the highest score, you reach the state with the higher score. I mean, you are playing optimally. Reach the state with the current score. You reach a state with another score. You keep the one where you reach the state with the higher score. Yeah. Oh. I wonder. Maybe I actually need to have two different results table. The highest score that you reach a state with and the lowest score you reach a state with. Then what? How would I use that with the backtracking? The highest score you reach a state with and the lowest score you reach a state with. So so would choose Alice would choose between hmm, 1, 2. Bob would want to have reaching a let's say the state only scores Alice's score. But then it's not even about reaching the state with the lowest score because you could have a really low score and then on the final turn get all the points necessary. Like going up to a certain state with a low score doesn't necessarily mean that that's what you're trying to optimize for. What you're trying to optimize for is the win. Huh. 2-2. You reach the state of 2-2. So you reach the state with the last. Actually, you reach the state that's 1-1. Oh. Do 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 do. All right. Well, oh gosh, another medium that I can't solve. That's that's disappointing. All right.